All right, so last time we left off talking about the strength of the different acids and bases. And we said again that strong acids are 100% dissociated. Our weak acids are going to be partially dissociated. Very weak acids would have weak conjugate bases. And things that are not acidic could be very strong bases then. So we'll take a look in this section at how we actually start to measure acid strength or base strength. And this is using our dissociation constants. So these constants are going to give us a value for how much of the acid will dissociate at any one time. So the higher the Ka value essentially, the stronger the acid. So we have an acid dissociation constant. You could also have a basic dissociation constant too, a Kb value, that would indicate the strength of a base, for example. So for this, we're looking at the concentrations of the proton to the concentration of the anion, which is going to be negatively charged, over the concentration of the acid in the acidic form before it's dissociated. So we ignore the water because the water is actually going to be our solvent system, and so it is the main component of the system, and so it doesn't have much influence or doesn't change much in this process of dissociation. The things that change is going to be the state of our acid. So this is our acid. This is our conjugate base for that acid. So the only thing that's changed is the presence of that proton. So when it's absent, this is going to be our conjugate base. It can now accept a proton. And this is going to be the conjugate acid of the water molecule. So this is the base, the conjugate acid of that system. So we ignore the water within the system because it's so large. So the Ka value, or the dissociation constant, is going to be dependent upon the right side of the equation, how much of the compound is actually over here compared to how much of this acid is in the acidic form. So our Ka dissociation constant is the concentration of the hydronium ion times the concentration of our conjugate base, which is essentially the anion, and this is over the acid from the left side of the equation. So our strong acids are going to have Ka values that are much greater than 1. So this component up here is going to be much bigger than this component down here. And this is going to be because the dissociation is going to be almost complete. There'll be hardly any of the full acid left when you have a strong acid that's mixed in water. If the Ka value is much less than 1, this would indicate that dissociation is not favored and that you still have a substantial amount of the acid in the acidic form, that it hasn't dissociated that proton to the hydronium ion. So you can look at the Ka value and you can judge whether you have a strong acid or a weak acid just by the Ka value. So for example, if you look at some of our acids, we said our sulfuric acid, for example, is a very strong acid, and we'll see that that first proton will actually dissociate very quickly. So the Ka value for our sulfuric acid is very large. We can see that second proton comes off or dissociates a little bit less readily, and so our Ka value is 1.2 times 10 to the minus 2. So if we actually move this back, it would be 0.012 would be the Ka value. So you can see this is a much lower Ka value than the H2SO4. We see the same kind of trend for phosphoric acid. So remember, phosphoric acid is a triprotic acid. It's got the 3 hydrogens that can come off. The first one dissociates the most readily, and each subsequent one is going to come off a little bit less readily. And that's because you're developing negative charge on the phosphate group, and it's much more difficult for it to hold higher charge numbers than it is to hold a single charge. So that's why it's more difficult to dissociate the remaining hydrogens from this molecule. So our acetic acid is all the way down at 1.8 times 10 to the minus 5. So we'd have to move this decimal back 5 places to get this Ka value. So we said our acetic acid is a fairly weak acid, and in general carboxylic acids are much weaker acids than things like sulfuric acid or hydrochloric acid that have a very large Ka value.